Hey, College Algebra. In today's video, we're going to be talking about linear programming. And so linear programming has to deal with optimizing certain situation given restraints. And so within these restraints, you're going to get system of inequalities, and you're going to find the most optimal situation within all your solutions of the system of inequalities. Okay, so let's go ahead and figure out an optimal situation to this question right here. And so you need to buy some filing cabinets. You know that cabinet X costs $10 per unit. Okay, that's going to be important. And it also requires 6 feet of floor space, which you're going to need to know, and holds 8 cubic feet of files. So that's all of our information with cabinet X. Cabinet Y costs $20 per unit, requires 8 square feet of floor space, and holds 12 cubic feet of files. Okay, you have been given 140 to spend, but you don't have to spend all of that or that much. So there's going to be inequality right there. The office room has no more than 72 square feet of cabinets. How many of which model should you buy in order to maximize, so we're going to be maximizing here, storage volume. Okay, and so we want to be maximizing storage volume, and so here's storage volume for cabinet Y, and here is storage volume for cabinet X. And so we're going to want to set up an equation, 8x plus 12y is equal to our volume. And what we're going to want to do here is find the maximal volume that we can have within these restraints. What are some other inequalities that we can state? So here, cabinet X costs $10, Y costs $20, and we're given 140. So you can set up an equation, 10x, or a set up inequality, is 20y, is less than or equal to 140. Now it's less than or equal to because we don't have to spend all of it. The other one is square feet. So we have 6 square feet here, 8 square feet, and 72 square feet is the most we can use, but we don't have to use up all of it. So we'll set up another equation, 6x plus 8y is less than or equal to 72. Okay, the other one, there are 2 more inequalities that aren't exactly stated within the problem, but can be assumed. You can't buy negative cabinets, right? So X, or our file cabinet X, has to be greater than or equal to 0. And our file cabinet Y has to be greater than or equal to 0. Okay, so now let's represent this graphically. So I put our system of inequalities on this page, and now what I want to do is set Y by itself for our black inequality and our green inequality. So let's get Y by itself, and when we do that, we'll get Y is less than or equal to negative 1/2 x plus 7. You guys should be fairly proficient at getting Y by itself for these inequalities, so I'm just going to assume that you guys are capable of doing that. And so we do it for the green one now. So we'll get negative 3/4 x plus 9. Okay, so let's graph these. Start off with the black one. Our y-intercept is 7, and our slope's negative 1/2. So it's going to end up extending all the way out here. Okay, so now let's graph our green one. Y-intercept is 9. We're going to go down 3 over 4. So 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4. Okay, do this all the way down here. Okay, now let's graph our line. So we're going to have some intersection right there, and it's going to be crossing the x-axis here. Okay, but now we also have to worry about x greater than 0 and y greater than 0. So let's draw x right here, and and y like this. Okay, and now let's go ahead and fill in our inequality pieces, so whereas our shaded part. So for the black line, it's y is less than or equal to negative 1/2 x, so it's going to be anything underneath this line. And for the green line, it's anything less than or equal to 2. So go ahead and draw that. And all we're going to worry about here is the area where the shades overlap, right? Because our solutions can't be something that doesn't work for all of the inequalities. And so right here, this this blue line, I'm drawing all the inequalities for x greater than 0, y greater than 0. But anyways, all we're going to be worrying about is this shaded area right here. So I want to undo all this, make it clean. Okay, and so now that I've undid all of it, I'm going to go ahead and just shade in our area of solutions. Okay, so we're just occupied with this area right here. Okay, so good. We've graphed it. Now we have to figure out where or what is our optimal volume. So in order to find maximum volume, I'm going to go and rewrite what our volume is equal to down here. So we have 8x plus 12y is equal to v. Well, we can actually draw this as a linear line, right? Let's just get y by itself. When we do that, we'll have y is equal to negative 2 over 3x plus v over 12. Okay, so this is a linear line, right? Well, let's go ahead and plug in values for volume and see where a line goes through. And so let's try v is equal to 0. So let's put v or 0 into there. When we do that, we'll get y is equal to negative 2 over 3x. Okay, so let's go ahead and graph that. So down 2 over 3. I want to represent with the dotted line. Now this is a solution, right, because it ends up going to this corner right here. However, volume equal to 0 is definitely not what we want. We want to maximize it. And so we have all this other red shaded area that we want to try to figure out. So anyways, let's try a different volume. Let's go ahead, let's say volume is equal to 36. Okay, so we can rewrite this equation now. We plug in 36 to our v as y is equal to negative 2 over 3x plus 3. Okay, so let's go ahead and graph that. Now this line should be parallel to your first one because they have the same slope, which is going to make sense. Okay, so volume equals to 36 is obviously a much better solution. And first off, it's a solution because it goes through this red shaded area, but it's much better than a volume of 0 because then we're not getting anything. But let's try volume of 108 now and see if that'll help us out at all. So if volume equaled 108, let's go plug that into there. Y is equal to negative 2 over 3x plus 9. Okay, so let's graph that up here. It's going to have an intersection right here, and let's go ahead and graph it. Now notice that it never hits the red area. And since it never hits the red area, this is over our limit. And so we can say that v equals to 108 can be our optimal solution. So how do we find the optimal solution to be anyways? So I just want to draw those, give you guys an example of what it's going to look like. But to do this, what we're going to have to do is find our corner points. Here, there should be 4. Here and here of our shaded area, and plug those points back into volume, or into this equation right here. So plug in, oops. All right, so what are our corner points? So we have 0, 0, 0, 7. But now we have to figure out what these 2 points are. So how can we find the point on our x-axis? So the line, or the green line, ends up crossing there. And so whenever we're trying to find a value of something that crosses through our x-axis, our y value is going to be 0. And so here, when we're trying to solve for our x-intersect, we'll have 0 is equal to -3/4x plus 9. Now I changed it to equals to because it's just right on the line. We're not looking at the shaded area below it. So let's solve for x. -9 is equal to -3/4x. Okay, and so we'll get that when we multiply both sides by 4, or -4/3. Sorry, it's kind of getting a little cramped. We get that x is equal to 12. And so, since y is equal to 0, the point here is going to be, x goes first, 12, 0. Okay, but now we have to figure out the value of where those 2 lines intersect. So we do this using one of our systems of equations, one of our ways to solve a system of equations. So here I'm going to rewrite our green and black line, but I'm going to write them as equations because we're trying to find the intersection of the line, not the shaded area. And we'll also have y is equal to 1/2 x plus 7. Okay, so we've got that y is equal to one thing and y is equal to another. And where they intersect, they're going to have the same y, right? So let's just go ahead and say y is equal to y, or set each equation equal to each other. So -3/4x is now equal to the other equation. Okay, let's solve for x. Get all of the x's on one side and all the other numbers on the other side. Okay, and so I'm going to go ahead and change this 1/2 x to be 2/4. And so we'll get -1/4 x is equal to -2. And so we'll get x is equal to 8. Okay, we want to figure out our y now, right? So let's go ahead and put 8 in for x here. And so we'll get y is equal to -1/2 times 8 plus 7. And so when we do that, we'll get that y is equal to 3. Okay, so we got another point, 8, 3. Okay, we got our 4 points. Let's put them into our equation that solves for volume and solve. So here on this new slide, I have our 4 points and our equation for volume. So let's go ahead and put them in. So let's start off with 0. And so here, we'll just end up getting that volume is equal to 0. That's not optimal. But let's try this point next. So it'll be 8 times 0 plus 12 times 7, which is equal to which is equal to 84. So we can write 84 up here. Okay, but now let's try this point. So here we'll have 8 times 12 plus, oops, yeah, that's right, which is equal to V. So 8 times 12, that's going to be, let's see, 96 plus 0, and so we'll just get 96. So we get 96 here. Okay, so now our most optimal solution is to get 12 of those X cabinets. But let's try this last point and see which is optimal. So we'll have 8 times 8 plus 12 times 3. What's that equal to? So it's 64 plus 36, which is equal to 100. Boom, there we go. We've got our largest volume right here. And so our most optimal solution here is that we buy X, or 8 X file cabinets, and we buy 3 Y cabinets. So this is our most optimal solution right here. 8 X file cabinets and 3 Y file cabinets. Okay, so what have we just learned? You guys have just learned how to optimize a certain situation using a system of inequalities. So I posted another video on the blog, which will help you guys understand. The video goes a lot faster, but it also isn't more of a lecture, it's a tutor. So anyways, there are some questions on the blog I want you guys to answer. And what the question is going to be actually is, why do you think we just throw in the corner points into our volume equation instead of any of the other points? So why don't you think we throw this point in for volume, or this point, or even points within it? Why don't you think we throw those points into here to solve for maximum volume? Anyways, that's a question we're going to be discussing tomorrow, and I hope this video was beneficial for you guys.